In the realm of mathematics, one of the most sought after objectives by mathematicians is to generalize problems that connect with our intuition in the broadest sense possible. Usually, the way to do that is to start with a simpler case by analyzing one specific example that could provide us with useful insights into the problem and then building upon those insights to solve the problem in the general case. But every once in a while, we come across some peculiar problems that compel us to think in the opposite direction, and we find ourselves pursuing a general case of the problem in order to arrive at a solution of the special case. Now, as counterintuitive as that approach may be, it's truly one of the most underappreciated gems in the field of mathematics. Now, our aim for this video is to present a delicate problem-solving approach that connects two seemingly unrelated ideas in mathematics in an immensely satisfying way, and to demonstrate how the act of playing around with problems can lend itself to some awe-inspiring proofs. Here's a basic setup of the problem. Imagine an infinite sheet of paper with parallel lines drawn on it a distance of d apart from each other. If a needle of length L is thrown onto the sheet of paper, what is the probability that the needle intersects one of the lines? Now, the reason I find this problem especially fascinating is because pi shows up in the answer out of nowhere. The classic approach for solving a problem like this would be through calculus, which involves the use of integrals to evaluate the average value of the probability function over all possible outcomes. But the calculus proof simply fails to provide us with an intuition as to where the hidden circle in the problem is, and is largely incapable of connecting circles to the notion of throwing needles onto the sheet of paper. So, I'm going out on a limb here by abandoning this standard calculus approach in order to look deeper into the problem from a completely fresh point of view. If I was looking at this problem for the first time with no prior experience in calculus whatsoever, how would I go about solving it? Imagine throwing a single needle onto the sheet of paper. Let P of n be the probability of n intersections. Then, by definition, the expected number of intersections is equal to 0 times the probability that you get 0 intersection, plus 1 times the probability that you get 1 intersection, plus 2 times the probability that you get 2 intersections, and so on. We know that the needle can have at most 1 intersection. Hence, the probability of 2 or more intersections becomes 0, giving us the expected number of intersections is equal to the probability of a single intersection. The thing to notice here is that this result provides us with an alternate method for evaluating the probability of an intersection by calculating the expected number of intersections instead. But it seems like this shift in perspective doesn't get us anywhere, because now we have an even more challenging computation to make. Since we can't manipulate the constraints of the problem itself, perhaps now would be a good time to venture into some uncharted territory. How about we subdivide the needle into two distinct parts of length x and y such that x plus y equals L. Now, instead of thinking about the expected number of intersections for the needle as a whole, we can think about the expected number of intersections for both of these parts individually. So how would we go about doing that? Naturally, the first idea that might pop up in your head is to use a function, let's say capital X, to denote the number of intersections of the segment X, and another function, let's say capital Y, to denote the number of intersections of the segment Y on any random throw of the needle. To elucidate on this idea, every time you throw the needle and it lands in a certain position, the segments X and Y may or may not intersect with one of the lines. The purpose of capital X and capital Y is to provide us with that very information. Thus, the values of capital X and capital Y vary from outcome to outcome. In a sense, capital X and capital Y are functions defined from the set of all possible outcomes to the set of real numbers. In higher level probability, these kinds of functions are called discrete random variables. These functions are a very useful tool in approaching problems involving probability, as they allow us to quantify the outcomes of a random occurrence by assigning a numerical value to every single outcome. Right now, we don't have a lot to work with. So, instead of going down one specific path, let's just take the liberty to experiment and play around with the problem a little bit. When we're dealing with problems involving probabilities, instead of analyzing a single case in isolation, it's often useful to think about what happens over a sample of cases. Imagine throwing a large number of needles over a sheet of paper and consider all the needles that actually end up hitting one of the lines. Now think about what fraction of the total needles that would represent. Intuitively, you would expect this fraction to be more or less equal to the probability of a single needle hitting one of the lines. This provides us with a useful insight for approaching this problem. Instead of considering the probability of an intersection, why not explore the idea of the expected number of intersections? Let me explicitly formulate this question around this idea. Given a single throw of a needle onto a sheet of paper, what's the expected number of intersections that you will get? On first thought, this might seem like an even more intimidating problem to tackle than the one we started with. And it's not completely obvious why we would introduce the idea of expectations into the problem when the idea of probabilities was already hard enough to work with. Now, the answer to this question is gonna gradually reveal itself as the proof unfolds, and by the time you get to the end of the proof, I think you'll agree that using expectations instead of probability was a pretty reasonable decision. Since we have functions capital X and capital Y that tell us the intersections of the segments X and Y on any given toss of the needle, we can alternatively say that we want to evaluate the expected value of capital X plus capital Y. Now, how would we do that? Well, in order to make some headway into the problem, let us just go ahead and throw the needle onto the sheet of paper and see what happens. Now, I want to remind you that we're not headed in any specific direction right now. Instead, we're just giving ourselves the liberty to play around with the problem for a while just to see what happens. It may or may not lead us to something useful, but if there's one golden nugget in problem solving that I've really come to cherish over the years, it's the fact that when you're just beginning to approach an intimidating problem for the first time, the act of playing around with the problem with no specific goal in mind can go a very long way in building up the groundwork and foothold into the problem necessary for a more rigorous proof. So, with that idea in mind, you go ahead and throw the needle once, and lo and behold, you get an intersection at the very first attempt. The intersection comes from the segment X of the needle. So, for this particular outcome, you'd say that capital X is 1 and capital Y is 0. And the sum of our discrete random variables, that is capital X plus capital Y, takes on a value of 1. Then, when you go for a second toss, you see that this time you weren't as lucky, and the needle actually ends up with no intersections from any of the lines in the plane, meaning both capital X and capital Y are 0 for this particular outcome, and so is the sum of these two variables. But we're not going to give up so soon, are we? So we go for a third toss, and what can you say? You do end up getting an intersection with one of the lines. Only this time, it comes from the second segment y of the needle, meaning that for this particular outcome, our function capital X takes on a value of 0 and capital Y takes on a value of 1. And notice that this sum, capital X plus capital Y, also takes on a value of 1. Now, of course, three outcomes are not enough to provide us with any useful insights as to what's really happening in the problem here. But they do provide us with an overview of every possible way our needle toss could turn out. You could go ahead and toss the needle a couple more times, and you'll see that on every possible outcome, one of three things will happen. You either get no intersections at all, or you get precisely one intersection from the segment X or you get 1 from the segment y. That's it. Those are the only three possibilities. The only three ways our needle toss could ever turn out. Now, those of you who possess a greater attention to detail might point out that there's one more outcome in the experiment that we failed to account for. That is, the needle landing directly over one of the lines. The number of intersections in such a case would be infinite, and if it was possible, it would seriously complicate the computation of a probability. But if you are one of those people who did point that out, I'd like to tell you, rest assured, because the probability of such an outcome is zero. Between any two of those lines, there is a whole continuum of distinct positions that the needle could land in. And for every single one of those positions, there is a whole continuum of inclinations that the needle could make with the horizontal. In order to compute the expected value, or in other words, the average value of capital X plus capital Y over all possible outcomes, we need to figure out exactly how often these individual segments intersect with one of the lines. Now, ideally, if we were dealing with a single needle, this would be a pretty straightforward task. The expected number of intersections is simply the total number of throws multiplied with the probability of an intersection. But over here, things aren't as simple as that because now we've got two different needles attached together and being thrown at the same time. So the position and orientation in which the two segments land are not independent of each other anymore. Now, here comes the clever part. I want you to toss the needle again, but this time only focus on the segment X of the needle and try to imagine how or where this segment is going to land. While you're doing it, I want you to let your imagination run wild and think hard about how the outcomes of a toss are different for this smaller segment than for the needle as a whole. You'll realize that if the needle tosses are truly random, any smaller segment of the needle should behave exactly how the needle behaves as a whole. That is, every single position and orientation that the smaller needle could land in should be equally likely, which, by the way, is an informal way of saying the segment X has a uniform distribution over the entire plane. In a way, you could think about the segment X as being independent of the other segment Y in the sense that when you drop the entire needle, the smaller segment X is completely free to land wherever it wants and whatever angle it wants. But once it lands in a certain spot, the position and the angle of the segment Y are also fixed and cannot be altered. The neat part about this entire argument is the fact that now we can express the number of intersections of the smallest segment in terms of the probability of intersection without having to worry about the behavior of the needle as a whole. Now, in order to evaluate the expected value of capital X plus capital Y, we simply take every single result and multiply the value of capital X for capital Y for that particular outcome with its frequency. Once you do this for all possible outcomes, you simply add up these products and divide by n to get to the final answer. Now, you might feel like this entire process is quite reminiscent of the idea of taking a weighted average, but what's really happening here is that we're adding up the values of capital X plus capital Y over all possible outcomes by clubbing the cases with the same value together and then dividing by the sum by the total number of outcomes. Now, recall from before that there were only three different possibilities for the values of capital X and capital Y. The first possibility is that capital X equals 1 and capital Y equals 0. Now, here comes the neat part. Every time the segment X hits one of the lines, we can guarantee that the segment Y doesn't, and vice versa. So what this means is that in order to evaluate the number of outcomes where capital X is 1 and capital Y is 0, we simply need to determine in exactly how many of those n tosses the segment ends up hitting one of the lines. This number, as we calculated before, was equal to h1 times n. So, in our weighted average, we write 1 as the value of capital X plus capital Y, and we multiply it by h1 times n, which, as we know, is the frequency of this outcome. The second outcome is where capital X is 0 and capital Y is 1. Well, once again, we know that the segment y intersects with the lines exactly h2 times n number of times. So, by a similar argument as before, we write 1 as a value of capital X plus capital Y, and we multiply it by the frequency of this outcome, which happens to be h2 times n. Now, for the third and final outcome where both capital X and capital Y are 0, we know that this sum must be 0, so whether or not we count them into a sum really doesn't make a difference, because no matter what the frequency of this outcome is, when you multiply it by 0, the product comes out to be, well, 0. Now that we have the sum of the values of capital X and capital Y over all possible outcomes, we simply divide by the total number of outcomes to get the expected value of capital X plus capital Y. Now, as you might expect, the n cancels out, leaving us with h1 plus h2. Now, it might look like there's nothing particularly useful about this result, until you realize that the probability of an intersection is the same as the expected number of intersections. Well, if this is true for the entire needle, it must also be true for any given segment of the needle, following the same independence argument from before. So h1 is also the expected value of capital X, and h2 is the expected value of capital Y. Now we've got ourselves a pretty neat functional equation that tells us that the sum of the expected values is equal to the expected value of the sum, meaning essentially that we can split the expected value of a single needle into the sum of the expected values of its constituent needles. So where does this get us? Apparently, we've broken the problem down into two simpler problems, but the premise of these two problems is still identical to that of the original problem. So it's not completely obvious how going down this particular path could help us arrive at the solution. Well, truth be told, there's a lot more to this result than meets the eye. To begin with, I want you to imagine you have a needle of length L made up of n small segments, let's say x1, x2, x3, all the way up to xn. Using the functional equation that we just obtained above, we can write the expected value of L as the sum of the expected values of each of these individual segments. Now, I want you to imagine the limiting case where n tends to infinity. Essentially, we're imagining a needle with infinitely many fine line segments of negligible length. The length of the needle is proportional to the number of line segments it is made up of, which necessarily implies that the expected number of intersections is directly proportional to the length of the needle. Thus, the expected value of the needle of length x can be written as x multiplied by a constant c, where c could be any positive real number. Now, all that's left for us to do is figure out exactly what this constant is. Now, we're approaching the final act of the proof, and what we're about to pull off is going to require us to manipulate the very premise of the problem we're dealing with. The functional equation that we derived for the straight needle before is actually perfectly valid for any two discrete random variables, capital X and capital Y, regardless of whether or not they're independent of each other. This is a very standard result in higher level probability, and is known as the linearity of expectation. I'm going to go ahead and do something very counterintuitive. I'm going to generalize a problem for needles of any shape given that they're made up of individual line segments. Now, I know this feels like we're wandering into a wildly different direction when it's not even obvious how this is going to help us solve the special case where the needle happens to be a straight line. Well, it turns out sometimes stepping into the general case can lend us some ingenious insights into the problem that allow us to solve the special case. I want you to realize just how much freedom this remove constraint provides us into the problem, because now we can have needles in the shape of triangles or quadrilaterals or in general polygon of any number of sides, and as long as the total length of the needle stays the same, the expected number of intersections is not going to be altered. In order to evaluate a constant c, we just need to figure out a case where we already know the expected number of intersections. The obvious candidate for the job, as many of you might have anticipated already, is the shape of a circle, since it's the simplest case that you could imagine. However, there's just one small caveat. The needle can take on any shape we want as long as it's made up of straight line segments. The problem with taking a circle as a needle is that it's a continuous closed curve rather than a chain of line segments. In order to address this minor complication, we can simply imagine a regular polygonal needle of n sides and consider the limiting case where n tends to infinity. This essentially allows us to extend this expectation function to needles of any shape, including curves, like the circle. The neat thing about choosing a circle is that we don't have to worry about the inclination of the needle anymore, since rotating a circular needle changes absolutely nothing. The only thing we have to worry about is where the circle falls. Now, to finish off this proof, I've got one final trick up my sleeve. I'm gonna go ahead and consider a circle of diameter d. The brilliance in this idea comes from the fact that a circle of diameter d, when thrown onto a sheet of paper, is certain to intersect with the lines at exactly two different points, regardless of where it lands. This means that the expected number of intersections for this circular needle is precisely 2. Now, using a linear function to evaluate the same expectations, we take pi times d, which is the circumference of our circle, and multiply it by our proportionality constant c in order to get the expected number of intersections, which, by the way, we already know is equal to 2. Hence, the value of our proportionality constant must be 2 over pi d, giving us our expectation function. Now we finally come full circle, no pun intended. Now we can simply plug in the length of our needle L into the expectation function, and ladies and gentlemen, the probability of our intersection is equal to 2L over pi d.